Oh, really? Oh, I see. Oh, you just prompted him? Thank you. Thank you. That's good. Uh, so I guess I'll have to excuse him. Okay. I don't know. I made it years ago. I probably wasn't. I was just looking, you're looking for something to write down, and I'm like, hey, like, this sounds good. Okay, I think I got everyone. Don't distract me while I'm clicking absent people. Okay, there we go. Yeah, let's go ahead. This one was super easy, wasn't it? So the main thing that people get wrong with this one, I don't know why, because I try to make it super clear, but for some reason, some people want to put the age, the kid's age along this side, and then the grade along. I don't know why that is, but I even specified use age as your independent variable. Independent variable is the x-axis, this variable down here. So to make this look pretty for me, make sure you put age down here. Just a minute, I'll do that. So you have age down here, and then you have grade. And you might think that this is a weird thing to do, but my sister, I remember my sister being proud that she was able to figure out what grade a child was in based on their age. Uh, she's childless, and so she would see my children, and she would figure out what their grade was based on their age. So it is kind of strange. But anyway, so that's probably, yeah. So this is probably decades old. This looks kind of old, doesn't it? That font. No one uses that font anymore. But anyway, so let's go ahead and fill this in. It's not all that hard. Age is 8, grade is 3. And the calculation, by the way, age is 9, grade is 3, is approximately, the way that she did it is she said, approximately you subtract 5 from the age and you get approximately the grade. Sometimes you're off by a year, but whatever. So 7, a 7-year-old in first grade, a 10-year-old in 5th grade. So yeah, this is a little bit boring, isn't it? There you go. 8-year-old in 2nd grade. So yeah, you can see there's sort of a cluster here. And then a 16-year-old in 4th grade. Okay, well, I don't know. That's the outlier. So that actually brings, so if you have something like this, you're done. You've got 100%. And in fact, everyone who's here, I just did it right now. I put 100%. It was actually quiz 11. I found a blank quiz. There it is. So anyway, this though is one of the things we need to talk about today. This guy right here. Yeah, the outliers. So there are ways to determine, you remember in when we were doing box plots, there was this interquartile range, and you could do 1.5 interquartile ranges on either side of the box to figure out what outliers were. There's a similar thing that you can do with a scatter plot like this to identify outliers, but it's incredibly technical, and it's not super worth it, at least for us, but it exists. So just bear in mind that if you're ever doing this in some sort of advanced stats class, this thing, you can look it up. I'm sure that if you're in some sort of advanced stats class or advanced data research methods in psychology or whatever it is, that you'd be able to figure this out. Or maybe it would be part of the lesson, but it involves figuring out sort of what, like bands, if you will, and they would look something like that around the line of best fit. And we talked about the line of best fit the other day. So you have a line of best fit, you have these bands that are kind of like a 95% confidence interval, if you will. And so anything outside those bands, that's going to be an outlier. So this is something that I've sometimes included in teaching about and sometimes not. It is quite technical, but the main thing to note is that it does exist. Now, so that if you ever need to do this, you can look it up. You guys are smart. You can figure it out. Use your Googles, and I'm sure you can figure it out. On your homework, though, for next Wednesday, what you're going to be presented with is basically this. And you're going to be asked, are there any outliers? So, whoops. So can't I get rid of that pink? There it is. So on your quiz or on your homework, one of the things, there's like 3, you know how it is. Sometimes there's 1, sometimes there's 2. This time there's 3 objectives, but they're all super easy objectives. One of them is this, is can you tell whether there are outliers? And basically they just want you to visually see, are there outliers? So if this data looked like this, let's put it right there, then you'd say, no, there aren't any outliers. Everything's pretty much grouped in there. And then once you have a dot that's like kind of far away, it'll be obvious, don't worry. You know, it's Newton anyway, so if you get it wrong, you can just do it again. It's not that big of a deal. So here, I would say, okay, there's an outlier there. So, so that's the first thing for next time. Oh, but before we go on, we have Easter, and so as is my tradition, I always do this. Just a sec, can I find it here? There it is. So years ago, this is decades ago, 25 years ago, in fact, a new faculty member was hired, and maybe it wasn't quite 25 years ago, but she is still here. She's still on the faculty. And she emailed me a question. So she emailed me this question. Now, the reason why she emailed me this question was she wanted to go on, let's see, does it say? Here we go, yeah. Yeah, it pretty much explains itself. Hi, I'm a new faculty member, and my husband and I are interested in participating in mission trips over spring break. You know, it's great. This year, spring break overlaps with Easter break. My husband is a pastor, so we are unable to miss Easter at our church. Is spring break always scheduled to overlap with Easter? And I knew the moment I get this, that this was not intended for me. You see, back in the day, the chaplain was a guy by the name of Joe Noonan with an E. Noonan with an E. I'm John Noonan with an A. So you can imagine the confusion with this. You email someone that's, whoops, no. Let me go back a sec, just get rid of that. So here's me. It was MVNC back then. And here's Joe. He still worked here up to about 5 years ago, just before the pandemic, I think maybe 6 years ago. He quit. Anyway, so you can imagine the confusion. And the entire time, even after he left, I would get emails from students asking me to officiate at their weddings, and he would get emails asking, for help in math problems. Now, he was a little bit of a joker, and so he would actually try to offer help, which he knew was faulty. I would generally just say, no, I'm not the right guy. I mean, you don't want me officiating your wedding. You want this guy. So, but anyway, getting back to this. So I knew that this was probably not intended for me, but I thought, nonetheless, I'm a mathematician. I could help this person. Oh, by the way, also the academic schedule was different back then. We had a thing called January term. And so spring break did sometimes overlap with Easter. Easter because of the, Easter moves around. Spring break usually is in the middle. So here's what I did is I thought, I'm a mathematician. I can answer this. So, hey, I suspect you meant this email for Reverend Joe Noonan, but I'm Dr. John Noonan. As a mathematician, I can help you. The short answer is that spring break is always scheduled for the middle of spring semester. Easter moves around and is based on the phases of the moon. The probability that Easter will be during spring break is approximately 0.25. That's the short answer. The long answer, let's see, do I have it here? Yeah, the long answer, and then I don't have the entire text here, but I launched into this. So first off, we have to go back to Luke. And in Luke, it says that then came the day of unleavened bread, which is the Passover lamb had to be sacrificed. Jesus sent Peter and John saying, go and make preparations for us to eat the Passover. This is, of course, the Passover that Jesus ate, the Last Supper, so to speak. And so if we want to know when Easter should be, we need to know when Passover should be. And so we have to go all the way back to Leviticus. And Leviticus says, these are the Lord's appointed festivals, the sacred assemblies that you are to proclaim at their appointed times. The Lord's Passover begins at twilight on the 14th day of the first month. And the 15th day of the first month is the Lord's festival of unleavened bread begins, blah, 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 blah. So we know when Passover is supposed to begin, so we know when we should celebrate Easter. And so we have to go and figure out, well, when is this first month? It's the first month according to the Hebrew calendar. And so here's the Hebrew calendar. So the first month is the month of Nisan. And so the ecclesiastical or biblical calendar, that's the first month. And it's 30 days long. It's based on the phases of the moon. And it's generally in March or April, according to the Gregorian calendar. That's a whole other story, which I'll mention just briefly, why we have a Gregorian calendar. But anyway, So in March and April. So what is this business about a lunar calendar? Well, these months are based on the phases of the moon. So to figure out when we're going to celebrate Easter, what we'll do is we could do this. We just find the first Sunday, because this is the first month of the Hebrew calendar that began on the spring equinox. So the first Sunday after the first full moon after the spring equinox. That is the definition of when Easter is. Now, of course, church officials aren't satisfied with something that simple. I mean, that's kind of complicated. But so here's what the early church, maybe not early, this is after we switched over to the Gregorian calendar, they came up with this as a formula. So you have all of these things, and this is literally what church officials back in the, the whatever 900 AD, that's what they said. They said, now they didn't use this sort of notation. I'm using modern mathematical notation, but they said, go through all these calculations and then, apply this formula, and that's when Easter should be. But generally, Easter is just the first Sunday after the first full moon after the spring equinox. So let's find out, when should Easter be this year? Well, this year, the spring equinox every year is approximately the 21st. It moves around a little bit because of the wobble of but that's not, and also the leap years cause a little bit of a shift, but let's just go with the 21st. So let's go and find the first full moon after this, because the month of Nisan begins on the new moon, and so we want the full moon because that would be the 15th of Nisan. So let's see, we keep going. Here's April, and then, here it is, the 13th. So that was just this Sunday, we had a full moon. And so the first Sunday after this is that Sunday there. So there you go. So that's why Sunday is the 20th this year. Now, you might also know that the, wait, before I do that, sorry. Last year, I thought, it'd be really interesting to see what's the distribution of Easter. It's like, how late could Easter be? Because this is pretty late, isn't it? Well, it turns out that Easter could be as late as the 25th. That's the latest it could be. Here's a distribution of Easters from 1600 to 2100, according to the census, oddly enough. So I actually have a link here to the census where I got this data. And then I just put it into a little graph here. So this is the number of times Easter is celebrated on the 25th during those 5 centuries. Looks like 5 times during those 5 centuries, it's on the 25th of April. And notice that the earliest it could be is the 22nd. Of course, that would mean that there's a full moon on the spring equinox, and then the very next day is a Sunday. And that there's only 3 Sundays in those 5 centuries, which has March 22nd, that early Easter. And then the rest of them, it's pretty uniform, I think, in between there. Not very many late ones. So we're right here. This is pretty late in the game. So when people complain, it's pretty late, you can say, yeah, you can blame the lunar calendar. By the way, you might be wondering, when's the next time? When's the next time that we're going to get an Easter this late? 2038. So look forward to 2038. You're going to be celebrating Easter and graduation in the same weekend, basically. Well, maybe not quite, 1 weekend later. So there you go. Yeah, you don't care about the Julian calendar, so we won't do that. I think I've bored you enough. So thanks for enduring my my little thing about Easter. If you do have further questions, I'm happy to answer them later. But for now, we do need to move on to whatever it was that I wanted to do today, and that's correlation. So here we go. What are we doing? I had it on the right slide, and then I lost it. Okay, that's it. Yeah, that's what we're doing. Yeah, I had it, and then I switched. I got excited about Easter. So thank you for indulging me. Let's see. So calculating R. This is the correlation coefficient. So correlation. Yeah, by the way, there are 3 things you're going to do on your homework this weekend, this long weekend. You got 7 days to do this. You got plenty of time. Might as well do it today or maybe tomorrow. And one of those things is that whole thing about outliers. Can you visually see where an outlier is? Super easy. I don't think I need to do much there. The second thing you're going to be doing is you're going to be making predictions That's pretty easy too. We'll practice that in just a minute. The third thing is to compute correlation and determine whether it's a significant correlation. That's a little bit harder, so we're going to spend a little bit more time on that. So what is correlation? Well, we talked about it last time. We had it here. Oh, and there's that. Sorry, I just realized there's yet another fun thing. Okay, more statistics you can use later. But for now, let me remind you of this little nugget where we took our z-scores for our height and our z-scores for our shoe size. This is generally what is done. I mean, mathematically, it's what is done, is you do these z-scores and multiply them together and average everyone's together. And if you have a positive number, when you do that, it means that things are positively correlated, meaning that when one goes up, the other one goes up. When you have a negative number, it means the opposite, that when one goes up, the other one goes down. So let's see how we are going to do this in Excel. And you can either pull up your Excel or not. This is actually so easy. Oh, I wonder if my microphone is working. Oh, it is. It's always tragic when I get to the end of class and I realize, oh, the mic was off. No, this one is on. It's fine. Okay, so where is my linear regression? There it is. So if you want to, like I said, this is not hard at all to do. So you really don't, I mean, you could even just write down, I'll write what you want to write down to do this. I'll do it right here, in fact, calculating R. So how do you calculate R? Well, you're going to use, oh, it's actually on this. Here we go. So there's the hard way, the easier. There it is. So it's right there. In Excel, you use Corel. Oh, you can't see that. Okay, that's better. Okay, so in Excel, you use this Corel function. I'll actually show you how to do this, and you can try it yourself if you have your computer open. But like I said, no big deal if you don't, because this is a quickie, and then we're going to move on to the next thing. So, so let's actually take a look at these data. And what are these data representing? Just a sec. So this is from, okay, this is from the thing that is online. Oh, the movies and math. Yeah, we'll do the movies and math just for fun. So remember we did the movies. This is if someone watches one movie, they get a 10 on their math score and then so on. So here's how you do this. You just type equals Corel. And then it tells you what to do down here, but if you're confused, array 1 are the movies, and you can actually just do B:B. That's all the movies, including the ones that don't exist down here. And then comma, and then do the math scores. So you can actually do that, if you want to, just highlight the whole thing, or you can be more specific and just say, okay, the movies are going to be A or B2 through B whatever it is, and the math scores. As long as you have the same size of your, the ranges. Here, let's see, where is it? 16. So here, just to show you what I mean. Okay, so there's my correlation coefficient. Let me B2. Whoops, that's not what I wanted to do. B2, uh-oh. Try again. To B16, and then C2, just to show you that you could do it this way. So that you're just getting, it's the same thing, so that you just get the numbers that you care about. As long as there's nothing down here below your data, you can just highlight the whole column, it's fine. But the main thing is that you want these two to be the same size right next to each other. So what's the correlation coefficient? It's negative 0.966. That's a pretty big correlation coefficient. And by big, I mean it's close to 1 or -1. Correlation is always between 1 and -1. So here, let's jot that down. So R, some facts about R. R is always between -1 and 1. So that's the first thing. You're never going to have an R that's bigger than 1, just because mathematically, when we do these averages, it just turns out that you'll never get a number bigger than 1 or less than -1. The second interesting tidbit about R is that the closer to 1, whoops, yeah, we'll get to that map in a minute. The closer to 1, so when R is close to 1, what that means is that the dots are in a almost straight line. So you could draw dots like that, and they are going upward. So an upward slope, upward. So when R is close to 1, you're on an upward trajectory. Now, you don't know what the slope is, so by upward, I mean that it could be this, or it could be kind of less of a slope or a steeper slope. This only tells you how close you are to a straight line. When r is close to -1, I think you can probably guess what's going to happen here. You're going to be trending downward, and you're going to be very close to a straight line. So notice that those dots, so down, very close to a straight line. Now, what if r is close to 0? R close to 0, we'll go over here. It means that the dots are just scattered randomly around. There is no relationship between the two. So if you have something scattered all over the place, it just means that r, you have no correlation coefficient. If r is negative, you're going down, but once again, you don't know how steep. The steepness, the slope, that's a different issue. Just that they're all in a row, like all the ducks are in a row here. And then if it's close to +1, you're going upward. And once again, we don't know how steep the slope is, just that we're all going upward in a nice straight line. So when we go back here and we get an r value that is very close to -1, we should expect, and I think we did this last time, but I'm going to do it again. If we do the scatter plot, we should expect all the dots to be very close to a straight line. Let's go look at this. So we want this scatter plot here. And look at that. Those dots are pretty close. I know that there's this one. You might even say that's an outlier. But all the rest of the dots are very close to a straight line going downward. Beautiful straight line there. When we go back to some of the charts that we've looked at already, let's see if I can find this here. The Martin Luther King Jr. one, this one had a correlation that was very close to 1. It was like 0.975 or something like that, because everyone was very close to this straight line. Let's see, I've got some other ones that I can show you. Just a sec. That one doesn't have an R value on it. Here's some, just to get a sense for what it means for the R to be a different number. So, for example, if R is 0.54 or 0.58, both of those, not a very strong correlation, 0.5, but there is a trend. I mean, despite the fact that it's, this one's bigger than this, it almost looks like this has more of a trend than that. There is a trend that as the exam 1 goes up, exam 3 also goes up. So you have this trend. So same thing here with these two exams. There's a trend that goes upward. That's what we're looking for. That's what we're trying to understand with the thing. Oh, this is MLK. Oh, it was only 0.67? That would be higher than that. Oh, no, here it is. This is it, the 0.94. Okay, so this is the actual graph. That's a little bit higher. So do I have any others that we can look at? I've got another one. Yeah, I guess this one is fine. Just another homework versus final exam. And you have so I just wanted to show you what it meant for correlation to be a certain size. So you can see the trend line there. And this one has a correlation of 0.667. So I can see it on the next slide, but I won't show you the next slide. So 0.667. So you can see that the closer you are to 1, the closer the dots are to a straight line. Same thing with -1, -1 and 1. Well, I'm always on the lookout for correlations in the news. And this particular news story actually is from 2017, I want to say. Whatever year, I should know my history better. But the year that Russia invaded Crimea. I don't know if you remember this. This would have been when you were in, I don't know, middle school or maybe earlier. But Russia originally invaded Crimea, Crimean Peninsula. This is part of Ukraine. And then, of course, more recently invaded Ukraine itself, or started fighting with Ukraine, saying we want all of this territory because we're greedy. So anyway, a particular, I forget what, do I have the reference? Oh, I don't have the reference, darn. Anyway, one news organization thought that it would be funny to show people a map of the world and ask them 2 questions. Number 1, where is Ukraine? Number 2, on a scale of 1 to 10, how much do you think the US should intervene militarily in Ukraine? So you understand the two questions. One, where is Ukraine? Two, how much on a scale of 1 to 10 should we intervene militarily? So can you find Ukraine? Take a guess. I think what's confusing is that the colors, they don't have the, the Mediterranean Sea in blue, but you know where that is. But the Black Sea, you can't see where that is. It just looks like a country. All right, you got it? You got Ukraine? Do you know where it is? Okay, let me show you where Ukraine is. Here's Ukraine right there. I know. So yeah, you might have chosen this one or that one, or maybe you chose somewhere out here. Yeah, that's the Black Sea, by the way. And that little thing, that's the Crimean Peninsula, which is what Russia wanted because it was a nice port. However, here's the interesting thing about what I just mentioned. Here, oh, well, let me show you where everyone else clicked. So you might have clicked in your brain, but in this particular survey, people actually clicked this map. And here's where they clicked. I know, you can see that some people thought Ukraine was down here, or perhaps they thought that there was a town, yeah, I know there's a town down it's named Ukraine, Kansas, or something like that. So there's the places that people who did this survey thought that Ukraine was, and it's encouraging. It's encouraging that the majority are at least in the ballpark, aren't they? But here's the interesting thing about those two questions is that the further away, there was a positive correlation between distance and how much you want to intervene militarily. So the further you are away from Ukraine, the more you want to go in with the, and bomb them or whatever. Or down here, if you thought this was Ukraine, then you're like, oh yeah, let's go destroy them, or here. So there's a positive correlation between stupidity and wanting to go to war, apparently. So I know that's a little bit more political commentary, but yes. Oh yeah, yeah, there it is. Well, I don't know. Maybe they thought that Ukraine was an island in the very, very South Pacific. And you're getting close to Antarctica there, but very interesting. Yeah, I don't know if I know. Well, yeah, I guess. Yeah, no one thought that Mexico was Ukraine. They knew what Mexico was, right? Like, yeah, well, you got the USMCA, right? Or oh yeah, here we go. There's a few African countries. Okay, interesting. Okay, so here it is. If you really want the reference to this, I can probably dig it out. But here's their conclusion. The further our respondents thought that Ukraine was from its actual location, the more they wanted U.S. to intervene militarily, blah, 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 blah. All of these are statistically significant at the 95% confidence level. I just like to highlight that they're actually using statistics and computing things with statistics. So correlation in real life. So if you learn more, maybe you don't want to go to war. I don't know. Okay, so we've got that taken care of. So we've got correlation, and you can do correlations. Let's practice this one more time with this. So let me zoom back out so I know where I am. Example 2. Oh, I know which one I wanted to do. Example 3. Example 3, that's the one that I wanted to do. So let me explain what, say, example 3 is. And I was tempted. Last semester, I did this, and I was like, I really need to update this. But this semester, I'm like, oh, why bother? But here's where this came from. So years ago, this is like at least a decade ago, I went on Amazon and I just searched for television, and I went through, you know how you can like look at the list? I just went through and I picked the very first one that was a 9-inch television, and then the first one that was a 15-inch, and I just built this data set. And here's the size of the screen, and here's the price at least 10 or 12 years ago. Of course, this is absurd now because you can get a 96-inch television for about $500. Oh wait, there were tariffs that were just put on. Okay, $1,000 now. But anyway, at least it gives you an idea of what things were like 12, 15 years ago. I know we were suffering back then when we wanted a big television. We'd have to spend a lot of money. Yeah, nowadays you can just go to Walmart and get one for $250. But But anyway, this gives us a good idea to see if we can predict the size or the price of a television based on its size. And before we go any further with this, I have the data. It's on that spreadsheet. So if you really want it, it's in there on example 3. But here's the sort of thing that I'm going to be asking you to do on a test or on a homework set. And that is, number 1, can you decide which variable should be independent and which should be dependent? So in this case, we're trying to predict the price based on the size. And so we're using the size to predict the price. The thing we're predicting is the y variable, the dependent variable, and the thing that we're using is the independent variable. So independent variable is the size, and dependent variable is the price. So this is like bonus material because I don't think Newton has you actually spell that out. But that's the way it works. You want to make predictions. This is going to be important if you ever want to make predictions using your own statistics. We're going to make a scatter plot. Let's do that. Let's make this scatter plot. So you know how to do this. Highlight these data. There they are. And let's insert a beautiful scatter plot. Beautiful. There it is. We zoom out a bit so we can all see it. Okay, good enough. So I'm doing the best I can here. Okay, that's pretty good. So there it is. There's my scatter plot. So the next thing that we want to know is, and so let's see, I'll just check that off. There we go. So I'll toggle back and forth. Next thing, do you think there's a relationship between the variables? So take a look at my scatter plot if you were too lazy to make your own. Does it look like there's a relationship between the variables? What do you think? Yeah, seems like there's a relationship, doesn't it? So, but here's the thing that's interesting about this one. This doesn't look like a straight line, does it? Like if you were asked to put a line that goes through all those points, you'd probably put a line that was more curved. Like it's low, it kind of slopes upward and then it goes kind of up here. Do you think it would be a curve would be better than a straight line? Maybe exponential or some other curve like a polynomial, quadratic maybe. Yeah, so, but nonetheless, we're not into polynomial interpolation here. We're just going to do linear interpolation. So that's what the next thing to do is okay, so yes, so I'll put a yes with an asterisk, you know, because there does seem to be a relationship. Yeah, why or why not? Well, because all the dots are in a nice line, aren't they? But anyway, so there's a yes, but it's probably not linear, is it? But we're going to go on and barrel on ahead because this is, we want to find the linear. So to find this, this straight line, so I can't remember if it's this homework assignment or the next one, but one of them, you're going to have to find this least squares regression line. It's super easy. I know we did this on Monday, but let's do it again. You right click, add a trend line, and then see if I can see it. Display equation on chart. That's what I wanted to do. So I've got my equation. It looks like my mouse is working properly. I'm going to make this bigger so that we can all see it and enjoy it. There it is. Okay, so it looks to me, let me see, can I make this even bigger? Just a sec. Come on, buddy. What if I just delete that? Oh, yeah. Look at that, I can edit it. Okay, I just wanted to round to the nearest penny. That's why I did that. It was 29.497. It kind of bothered me. So how about that? 2950x minus 464. All right, there's our equation. We can use that to make predictions. So let's go ahead and make some predictions. So here we go. We've got our, here, let's see, I'll write it down. 29.5, I'll put it up here. Y is 29.50x minus 464.13. Let me just fix my 464. Okay, so here's our regression line. Beautiful. And so let's actually use this to make some predictions. So let's predict, there it is. Okay, we'll deal with this, the letter E in a minute. But let's predict the sale price for a 32-inch television. to do this, you're just going to take that regression line and actually plug in the number 32. So I'll leave this up here so that we can do this. And I'm going to dig out my calculator because I don't want to do this part in my head. Apparently this one has dead batteries. So I'll just put it back. I know I shouldn't do that. Here, I'll put it here. I'll deal with it later. Let's see, does this one work? Batteries are low. Well, as long as they last another 2 weeks, I'm happy. Okay, so let's see, 29.5 times 32. So here's what I'm doing is I'm going to take 32 and I'm going to stick it in there. And I'm going to predict the price of a TV that's 32 inches, which I realize if you went, I don't think you could buy a 32-inch television these days, could you? They'd call it a computer monitor. It'd be so small. But so anyway, there it is, 29.5 times 32 minus 464.13. And I got 479. So let's see. I'll do it up here. So this 32-inch is 479.87. That's the prediction. Okay, let's do the same thing for the 50-inch television. And to do the 50-inch television, so this is the sort of thing that you'll have to do on your homework this weekend. You'll be given the regression equation. You just have to plug in the number and interpret it. You'll say, oh, this is how much the 50-inch television will cost. So let's see. Entry, give me a sec. I'm going to do the same thing that I just did, but put 50 in there. And I got $1,010. That's incredible, isn't it? Nowadays, if you spend that much money, you know, you better get your, I mean, it'd be better to just buy an iPhone for that instead of a television, right? So anyway, there it is. Those are the predictions. Now, here's an interesting thing. I don't have it on here, but let's predict a 20-inch television. So let's do the same thing, but for a 20-inch television. So let's plug 20 in here. So let's do 20-inch television. Oh, that's still not small enough. I got 125. Let's try again with a 15-inch television. I just want to get a nice small screen because, you know, I'm going to put it in my truck. Oh, negative $21. That's it. I knew that I'd get negative sooner or later because of this number here. That if you put 15 in here, you get a negative number. You get negative. So they're going to pay you to take this little tiny screen off of their hands. Now, of course, the reason for this is because this particular regression equation dips down below the x-axis. It has a negative y intercept. The y-intercept, by the way, in this case, would be how much you would pay for a 0-inch screen, which doesn't make a lot of sense. But anyway, this dips down below the x-axis. So that's why we get this. Now, I'm kind of curious, though, to see what would happen if we shifted and did either what Hayden was suggesting or what I was suggesting and use a different type of trend line. Let's see, can I do that? Can I just click this? Just a sec. So when you do insert a trend line, why is it not clicking? Trend line? Format. Oh, there it is. Okay, you get all of these options over here. You can do exponential. Oh, that looks pretty good. Yeah, I kind of like that one. Let's see, can I get rid of the equation? And there's the correct equation, very nice. Or maybe you think, well, it would be better if it was a polynomial. Polynomial, yeah, that looks a little bit better to me, personally. See, the problem with exponential is all of you scientists know that exponential grows incredibly fast. So if you had a 100-inch television, it's astronomical what a 100-inch television would cost using that. Whereas polynomial, not as bad. So there are other ways to estimate this. A power function, that's interesting. And then what other ones? We've got linear, logarithmic. That looks terrible. But anyway, each one of these uses, that's weird. The weird, yeah, I don't like it. Yeah, so I think I like the polynomial the best myself, but on your homework, you're going to be dealing exclusively with linear regression functions. Okay, we have to deal with one more thing, and that is this right here. This question at the very top, letter E. Find the correlation coefficient, and is it significant? Whew, what does that even mean? Okay, let me show you what it means. So first off, correlation coefficient. Let's grab it. Move this stuff out of the way. You know how to do this. You do equals, Correl, highlight the sizes, and then highlight the prices. So we've got that. So 0.94, that's the correlation coefficient. Correlation, whoops, is 0. I'm writing it on the screen. I know you can't see, but I need to have it there for future reference. So as far as whether it is significant or not, and I am sad I don't have the table here. I have the table on the, just a minute. I'll grab the table from another place. Give me a sec. But what you're going to do is you do something similar to what you did for chi-squared. So we're going to give you a table. I'll show you the table and then explain how to interpret it. Give me a sec here. I just have to find the, I might have to just go right to the source. One more try. Correlation. See if this has it. That one doesn't have it. Try this one. Yeah, bear with me. Oh, here, this one probably. Does have it? Oh yeah, this one has it. Here. I'll put this up on the screen. Give me a sec. Come on. Double click, triple click. How many clicks do I need? Okay, this is a final exam I gave a few years back. It'll be similar to yours, but the table that you'll have, where is it? There it is. There it is. There's the correlation table. We zoom in so that we can see this. Don't worry, you'll have a copy of something similar to this in a bit. There it is. So we have degrees of freedom. You know the drill. We always have a bunch of degrees of freedom, and it's always but here it's part of the table. It says take the number of points minus 2. So number of points minus 2 is degrees of freedom. Critical value is listed here, and you'll see the same thing on Newton when you have to answer these questions. So what we're going to do is we're going to first of all figure out the degrees of freedom, and it says degrees of freedom are number of in the sample minus 2. So let's find out how many did we have here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So n is 11. Degrees of freedom is 11 minus 2, which is 9. So 9 degrees of freedom. So 9 degrees of freedom. Now the critical values, I believe that this is for a 95% confidence interval. In other words, 5% alpha level. I'm not sure if the one on Newton has a different, has more columns than this, but this is sufficient for us for now. So I'm going to go down and find 9 degrees of freedom, and I get 0.602 is the critical value. So let me write that down. Critical value is plus or minus 0.602. So see how I got it right off the table. So here's how you use that. The critical value, it's going to be the same as the way you used it with the chi-squared, where if you have a number that is more extreme than this, then it is significant. So you're looking for something bigger than this, either bigger in the positive direction or the negative direction. And so in this case, my R is this, and R is actually bigger than 0.602, which was the critical value. And so this is significant. It does pass the test. Let me just show you what the homework is going to look like, and then we'll be all done. Yeah, oh, 8:40. We got plenty of time. So give me a sec. Let me grab this. There, objectives. It's this one that I want to show. Can I just do that? I think I have to click through. Just a sec. So it's not due until next Wednesday. I know this is going to be a little annoying because I can't get to the actual problem I'm interested in, but not to worry. So this first thing, finding outliers, that's easy enough. Yeah, I'll just cheat on this one. So there's one type of problem that I want to make sure that we see. Predicted number of minutes. Okay, whatever. That's easy enough. Okay, so because you're making predictions based on the least squares regression line. Oh, this business. I hate this. Sorry. It's just the way that the wording is kind of weird. Okay, let me explain briefly what this means. So, so what they're referring to here about the estimate being reasonable and unreliable or reliable. So reliable, what they're referring to there is if you're making a prediction for a number that is within your range of observed data. So like if your prediction is for a time that is between 30 and 60, then we would say that it's reliable because you're interpolating, you're in between your actual data. If you're outside your data like this, it's unreliable. As far as reasonable goes, that's more like, is it reasonable? Would you say it's reasonable to say that, wait, 27, sorry, 27 is what is over here. So 27. So 27 is outside this range, 27. And then the reasonable part is referring to this number, the actual prediction. Is that a reasonable number? Like if that was a negative number, for example, not reasonable. If it's like more minutes than there are in the day, that's unreasonable as well. So that's all they're referring to there. Okay, so I'd forgotten about that. So when you get to that, it's pretty straightforward though, and you can always just get it wrong and then get it right the next time. So that's, oh, here it is, finally. There it is. So this is the sort of thing that, that you're gonna have to deal with. So let's try this one. It says that you've computed R to be 0.659. The number of data points is 32. We want to know if R is significant. Degrees of freedom is n minus 2. So 32 minus 2 is 30. So we're going to use this one, 0.349. So is this bigger than 0.349? It is. So this is significant. The language is a little bit weird, so that's why I wanted to show you this. Notice what they do here is they say, okay, it is significant, so it's either this one or this one. And so it's actually the second one, because notice that R is significant because it is not between the positive and negative critical values. In other words, if you were to draw the, here, we'll just put this up here. If you were to draw this on a number line, you would have the critical values like this. So the critical values were like plus or minus 0.3 something. And your R value was 0.6 something. So if you drew this on a number line, you would have 0 here. One of the critical values is 0.3. The other one is negative 0.3. And as long as you're outside, that is your more extreme, so here's your R value. As long as you're outside this range, it means that you have a significant correlation. If you're inside this range, you don't have a significant correlation. So yeah, just when I was looking at this, I thought, you know, that the way that they write that is kind of funky. So if you get it wrong, though, of course, you know Newton, you can just try again. But that's the right answer there. So there it is. All right, let's pause and hope you have a blessed Easter.